Hello, welcome to our presentation for the 8th Undergraduate Research Competition, and our presentation is about earthquake-resistant rainforest concrete structures.
I'm Ghada, an architecture engineering student at level 6.
And I'm Linah Salih, I'm a level 6 architectural engineering student.
Ahlam Basaad, architecture engineering student at level 6.
And I'm Ghaida Alsharif at level 6 architecture engineering student.
Starting with the introduction to seismology, seismology is the study that involves studying the source, size, and mechanisms of earthquakes. And seismic hazards are important for engineers to calculate the probability of ground motion and propagation given the size, motion through time and distance of the site. There are many types of seismic waves, but the main ones are the primary waves or the P waves, and they are the dominant type, and they are also called the body waves, considering they occur faster before the other types erupt with higher frequency. The secondary waves or the S waves are the waves we feel when earthquakes erupt. Second of all, talking about Reed's elastic rebound theory. The geologists concluded that the strain energy stored in rocks accumulate and cause earthquakes due over-amassment. The rock behavior depends on the stress it undergoes, so it either goes back to its original shape or it will deform, explode, and change its shape and or volume based on the magnitude. The causes of earthquakes mostly are heat and elasticity. That's why engineers develop seismic structure based on the rebound theory and further analysis for the structure to resist seismic waves and ground motion. Finally, talking about the surface waves, they are easily distinguished on the seismogram owing to its high amplitude, and it is responsible for further damages caused by earthquakes. There are two types of surface waves, starting with the relay waves. It spreads vertically and horizontally in ripples or form of rolls like ocean waves and can be most noticed in large spaces. The second one is the love waves. They move on a horizontal plane, causing damage on the foundation of the structures. They also travel faster than the relay waves.
So it's Ghada again. I'm gonna move on to the earthquake size. Each earthquake released enormous amount of energy that cannot be calculated without these three main factors. So first we have the earthquake magnitude, and that depends on the time and location. And the most common way to measure it by using Richter magnitude scale. So basically this takes the logarithm of the ground displacement as measured by seismograph, and then applies the correction which is varies with the distance from earthquake to the seismograph. But nowadays the most modern scale is the moment diagram scale, which can be used for a wide range like for magnitude and distance. And here the schematic showing how the magnitude affected the range of shaking. So moving on to the second point. Another way to measure the size of an earthquake is to compute how much energy it released. The amount of energy radiated by the earthquake is a measure of the potential for the damage to man-made structure. An earthquake released energy to many frequencies, and in order to compute an accurate value, you have to include all frequencies of shaking for entire event. Here is an example in this figure. And finally, the earthquake intensity, whereas the magnitude of an earthquake is one value that describes the size. There are many intensities value for each earthquake that are distributed across the geographic area around the earthquake epicenter. The intensity is a measure of shaking at each location, and it varies for place to place, depending mostly on the distance from the area. But however, there are many more aspects of the earthquake and the ground shakes that affect the intensity at each location, such what the direction the earthquake at, and also what type of surface geology is directly beneath you. This pictures show the shaking amplitude recording on 3 different seismometers. All 3 situations are about the same distance from the earthquake to the south, but the type of local geology beneath the instrument influences the amount of shaking at the location.
Moving to the site effect, previous earthquakes have shown that the site condition has a substantial impact on building damage. The intensity and the length of time of motion of a structure due to an initial seismic shock is related to the type of ground on which the foundation are built. So there are three main types going under the site effect, starting with the soil effect. The local soil condition influence the seismic motion that approach structure on the Earth's surface. The building foundation subsurface soil layers may amplify the building's response to earthquake motion originating in the bedrock. For the lateral discontinuity effect, seismic waves travel more quickly in hard rocks than in softer deposits. Sites with softer soils are also more vulnerable to higher shaking. The intensity of damage is greater in narrow zones along lateral discontinuity due to the soft material in these areas. And some general effects that might happen are, as the horizontal extent of the softer soil increases, the boundary impact of the bedrock on the site response decrease. Also, changes in the soil type within the site have an impact on the reaction locally within the site. A structure built on such ground may sustain significant damage. Lastly, the site topography effect. As known, the building located at the hilltop suffer treble more damage than those located at the base. Additionally, there is also strong instrumental evidence that the amplitude and frequency contents of ground motion are significantly affected by the surface topography.
Now moving to the structure system, starting with the definition. The structure system is a method of constructing the element of a building in which they design and build to resist different load, also transfer the load safely to the foundation. The structure system are categorized based on three different factors. Firstly, the material. Secondly, its way in resisting lateral load. And thirdly, the quality of seismic resistant design. Then moving to the structure design criteria, there are several criteria such as the datum, temperature, and the design loads. Moving to the next point, the structure analysis procedure. The method of structure analysis in earthquake has three categories. Start with the category A, which is a general recommendation, which means develop a guidelines for a dynamic seismic analysis that the designer can use. Category B, structure modeling, and category C, computer program development. Moving to the design of a concrete structure, the most important design concept is the strength. So as the steel has a good resistant in tensile forces generated by an earthquake, and the concrete capability to resist the compression makes the reinforced concrete a perfect material in earthquake areas. Moving to the next section, concrete design requirement, starting with understanding the concrete behavior. So in the figure we can see at A and B a normal beam, elevation and section. Then at diagram C we can see the distribution of the stress and the strain. Then at D we can see the beam under an increasing load and how the cracks are start to show. Then in E we can see the distribution of the strain and stress near to the crack section. Finally, we can see the distribution near to the ultimate load. Moving to the requirement of the seismic design. A seismic design category could be defined as the classification given a structure depend on severity of the design, earthquake, ground motion, and its occupancy. It has a category from A to F. Each one of them has a different corresponds to the ground shaking. And for the last point we have, which is the shear walls. Starting with a small definition, the shear walls are used to resist a heavy horizontal loads such as earthquakes or a high wind. It can be used in stairways or elevator shafts. And when a failure happens for the shear walls, the collapse of the structure is possible. So we have several types of failure. We can see in the figures the sliding shear failure and the flexural failure and diagonal failure. It could be in tension or compression, and finally the hinge sliding failure.
In conclusion, reinforced concrete structures are developed and used based on seismic calculations to prevent structure fault or damage.
Thank you so much for listening, and we hope you enjoyed this presentation.